The UFER ground that was installed is likely adequate for a 200 amp service. UFER grounds are typically designed to provide a low resistance path to earth for grounding electrical systems. They are installed by embedding a continuous metallic grid or strip into the concrete footing or slab of a building. The UFER ground that was installed is connected to the grounding electrode system of the main panel via the number 6 ground wire, providing a redundant grounding path. Since the copper pipes are connected to plastic below grade, they do not provide an effective grounding path. The plastic material acts as an insulator, preventing the flow of electrical current. Therefore, the grounding through the water system is not reliable. To ensure proper grounding for the new porch slab, it is recommended to install a UFER ground there as well. This will provide a dedicated grounding electrode for the porch and will not be affected by the type of piping used. Alternatively, a ground rod could be pounded into the earth next to the porch and connect it to the grounding electrode system. Once the UFER ground is installed for the porch, it can be connected to the water system. This will provide a parallel grounding path and enhance the overall grounding system. It is essential to ensure that the water system is properly bonded to the electrical system at the main panel. The UFER ground that was installed for the garage is likely adequate for the 200 amp service. However, since the copper pipes do not provide a reliable grounding path, it is recommended to install an additional UFER ground or ground rod for the new porch slab and connect it to the water system. This will ensure a comprehensive and effective grounding system for the entire property. The purpose of a grounding electrode system, which includes the UFER ground, is to provide a low impedance path for fault current to return to the source. This path helps to ensure that overcurrent protective devices, such as circuit breakers or fuses, will operate quickly and safely in the event of a ground fault. A UFER ground, also known as a concrete encased electrode, is a type of grounding electrode that is encased in concrete. It typically consists of at least 20 feet or 6.1 meters of bare copper conductor, number 4 American wire gauge or larger, encased in at least 2 inches or 50.8 millimeters of concrete. The concrete must be in direct contact with the earth. The UFER ground is an effective grounding electrode because the concrete helps to protect the copper conductor from corrosion and provides a large surface area for contact with the earth. This results in a low impedance path for fault current. Ground rods are another common type of grounding electrode. They typically consist of a copper or copper-clad steel rod that is driven into the earth. Ground rods are typically 8 feet or 2.4 meters long and 0.5 inches or 12.7 millimeters in diameter. The number of ground rods required depends on the soil resistivity at the site. In general, at least 2 ground rods are required to provide a low impedance path for fault current. The size of the grounding electrode conductor that connects the grounding electrode to the electrical system is determined by the size of the service entrance conductors. National Electrical Code, or NEC, Table 250.66 provides guidance on the size of the grounding electrode conductor. It is important to ensure that the grounding electrode system is properly installed and maintained to ensure electrical safety. The grounding electrode system should be inspected periodically to ensure that it is in good condition and that all connections are tight and free of corrosion. If the grounding electrode system is damaged or corroded, it should be repaired or replaced immediately. In addition to the grounding electrode system, it is also important to ensure that all metal parts of the electrical system are properly bonded together. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault current. This helps to ensure that overcurrent protective devices will operate quickly and safely in the event of a ground fault. Metal parts of the electrical system that should be bonded include metal conduit, metal enclosures, metal equipment frames, and metal water pipes. The size of the bonding conductors is determined by the size of the circuit conductors. NEC Table 250.122 provides guidance on the size of the bonding conductors. It is important to ensure that all bonding connections are tight and free of corrosion. Bonding connections should be inspected periodically to ensure that they are in good condition. If bonding connections are damaged or corroded, they should be repaired or replaced immediately. Grounding and bonding are essential for electrical safety. By properly grounding and bonding the electrical system, the risk of electrical shock and fire can be reduced. Here are some additional details regarding UFER grounds. Firstly, they are recognized by the National Electrical Code as an effective grounding method. Secondly, they offer a stable, low-resistance connection to the earth. Thirdly, they are less susceptible to seasonal variations in soil moisture compared to ground rods. Fourthly, proper installation is crucial, ensuring the concrete is in direct contact with the earth without any insulating layers. Fifthly, the minimum requirements include at least 20 feet or 6.1 meters of number 4 American wire gauge bare copper conductor encased in concrete. Sixthly, the concrete must be at least 2 inches or 50.8 millimeters thick. Seventhly, UFER grounds are typically connected to the main electrical panel using a grounding electrode conductor of appropriate size, as determined by the NEC. Eighthly, supplemental grounding electrodes like ground rods or ground plates may be required in addition to the UFER ground depending on local codes and soil conditions. Ninthly, regular inspection and maintenance of the grounding system is essential to ensure its effectiveness and safety. Tenthly, it is important to consult with a qualified electrician to ensure proper installation and compliance with all applicable codes and regulations. Regarding ground rods, firstly, ground rods are a common and widely accepted method for grounding electrical systems. Secondly, they provide a direct connection to the earth, helping to dissipate fault current and protect against electrical shock. Thirdly, ground rods are typically made of copper or copper-clad steel and are driven into the ground to a specified depth. Fourthly, the depth and number of ground rods required depend on factors such as soil resistivity and local electrical codes. Fifthly, in areas with high soil resistivity, multiple ground rods may be needed to achieve the required grounding resistance. Sixthly, proper spacing between ground rods is important to avoid overlapping of their effective grounding zones. Seventhly, ground rods should be installed at least 8 feet or 2.4 meters apart. Eighthly, the connection between the ground rod and the grounding conductor must be secure and corrosion resistant. Ninthly, regular inspection and testing of ground rods is recommended to ensure their continued effectiveness. Tenthly, it is important to consult with a qualified electrician to determine the appropriate type, size, and number of ground rods for a specific application. Now let us consider the connection to the water system. Firstly, connecting the grounding system to the water system can provide an additional grounding path and enhance overall grounding effectiveness. Secondly, however, it is essential to ensure that the water system is metallic and provides a continuous conductive path to the earth. Thirdly, plastic pipes or non-conductive fittings can interrupt the grounding path and render the water system ineffective as a grounding electrode. Fourthly, the connection to the water system should be made within 5 feet or 1.5 meters of where the water pipe enters the building. Fifthly, a bonding jumper should be installed around any insulated joints or non-conductive sections of the water pipe. Sixthly, the size of the bonding jumper should be determined based on the size of the grounding electrode conductor. Seventhly, it is important to verify that the water meter is also bonded to the grounding system. Eighthly, in some areas, the use of the water system as a grounding electrode may be restricted or prohibited by local codes. Ninthly, it is crucial to consult with a qualified electrician and local authorities to determine the requirements for grounding to the water system in a specific location. Tenthly, regular inspection and testing of the water system grounding connection is recommended to ensure its continued effectiveness. A final thought on supplementary grounding. Firstly, supplementary grounding electrodes, such as additional ground rods or ground plates, can improve the overall grounding system performance. Secondly, these electrodes provide redundant grounding paths and can help to reduce the grounding impedance. Thirdly, supplementary grounding electrodes are particularly beneficial in areas with high soil resistivity or where the primary grounding electrode is not sufficient to meet the required grounding resistance. Fourthly, the number and placement of supplementary grounding electrodes should be determined based on site-specific conditions and electrical codes. Fifthly, supplementary grounding electrodes should be installed at least 6 feet or 1.8 meters apart from each other and from other grounding electrodes. Sixthly, the connection between the supplementary grounding electrodes and the grounding system must be secure and corrosion resistant. Seventhly, it is important to ensure that all grounding electrodes are properly bonded together to create a common grounding system. Eighthly, regular inspection and testing of supplementary grounding electrodes is recommended to ensure their continued effectiveness. Ninthly, a qualified electrician should be consulted to determine the need for and proper installation of supplementary grounding electrodes. Tenthly, remember that local codes and regulations may dictate specific requirements for supplementary grounding electrodes. A deeper dive into bonding requirements. Firstly, bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. Secondly, proper bonding helps to minimize voltage differences between metallic parts and reduces the risk of electrical shock. Thirdly, all metal enclosures, raceways, and equipment frames must be bonded together. Fourthly, bonding conductors must be sized according to the requirements of the National Electrical Code. Fifthly, bonding connections must be made using approved methods and hardware. Sixthly, bonding jumpers should be used to bypass any non-conductive sections or fittings in metallic raceways. Seventhly, gas piping systems must be bonded to the electrical grounding system. Eighthly, structural steel in buildings must be bonded to the electrical grounding system. Ninthly, it is important to ensure that all bonding connections are tight and free of corrosion. Tenthly, regular inspection and maintenance of bonding connections is essential to ensure their continued effectiveness. Next is a discussion about inspection and maintenance. Thirdly, regular inspection and maintenance are essential for ensuring the continued effectiveness of grounding systems. Secondly, grounding connections should be visually inspected for signs of corrosion, damage, or looseness. Thirdly, grounding electrodes should be tested periodically to verify their grounding resistance. Fourthly, grounding conductors should be checked for proper size and condition. Fifthly, any damaged or corroded grounding component should be repaired or replaced immediately. Sixthly, grounding systems should be inspected and tested after any electrical work is performed. Seventhly, records of grounding system inspections and tests should be maintained. Eighthly, qualified personnel should perform grounding system inspections and maintenance. Ninthly, it is important to follow all safety precautions when working on grounding systems. Tenthly, regular inspection and maintenance can help to prevent electrical hazards and ensure the safety of people and property. In summary of electrical safety, firstly, electrical safety is paramount in all electrical installations and maintenance activities. Secondly, always de-energize electrical circuits before working on them. Thirdly, use appropriate personal protective equipment, or PPE, such as gloves, eye protection, and insulated tools. Fourthly, follow all applicable electrical codes and standards. Fifthly, never bypass or disable safety devices. Sixthly, be aware of potential electrical hazards and take steps to mitigate them. Seventhly, if you are not qualified to perform electrical work, hire a licensed electrician. Eighthly, educate yourself and others about electrical safety. Ninthly, regular inspection and maintenance can help to prevent electrical accidents. Tenthly, remember that electricity can be dangerous, so always exercise caution and common sense. It is important to remember that the information provided here is for general guidance only and should not be considered a substitute for professional advice. Electrical codes and regulations vary by location, and it is essential to consult with a qualified electrician and local authorities to ensure compliance with all applicable requirements.